We are going to cover concavity. Okay, so the idea behind it, we let f of x be some differentiable function. Yeah, not represented. It just actually is. Be a differentiable function on an open interval I equals the interval from A to B. Okay, so the graph is called concave up or concave upward if the entire graph lies above the tangent lines. For the entire interval. So if we were to graph that, let's say you have some graph there, and if you were to draw out the tangent lines for every point of that graph, just between whatever this A is and whatever B is, that's the tangent line there, that's your tangent line there, and this is where your slope is equal to 0. Say this is your tangent line, and so on and so forth. The entire graph is right on top of each and every one of those tangent lines. So this is a concave up graph. I'll write it so I won't run out of room. Okay. Now it's concave down if the entire graph between that interval is below all of your tangent lines. For the entire interval. Okay. Now, if we were going to draw the description of this one, say you have some graph between A and B, and this one we can make that between A and B. So this is between some A and B. And here, if we were looking for the tangent line at that point, it would be right on the outside. Same thing here. If you were looking for when the slope is equal to 0, it's right on the outside. Same thing here. Okay. So each and every point between that interval is right below each of the tangent lines. So this would be concave downward. Normally my way of remembering one from the other is concave up looks like a cup. So concave up, C up. Just my own little hint. You have a really bad memory, you get creative. All right. Any questions on that so far? So now we'll get the actual definition of concavity. That was just the general idea. Okay, so if f of x, some function f of x is differentiable across the entire graph or between the interval of a and b, so we'll let it be differentiable on the open interval from a to b. Okay. So in other words, we know that the graph is concave up if the derivative is actually increasing across the entire interval. And it's concave down if it's decreasing across the entire interval. So if f prime of x, clean that up a little bit. So what they mean by increasing and decreasing is, let's say if you have a concave up and a concave down. It doesn't have to be perfect, just any random looking graph. Okay, so we know here this is concave up. Let's say we start with a few random tangent lines. Okay, we do the same thing here, just a few random tangent lines. Okay, so if you notice for your concave up, this slope is starting down, just a deep slope. But as it goes to the right, it's not as negative. Then at some point it's going to equal 0. Then at some point it becomes positive, and it gets a higher slope and a little bit higher. So the slope is just steadily increasing between those 2 points. If you notice here, it's starting facing a pretty high slope. But then as it goes to the right, the slope lowers, and it's decreasing. At some point it equals 0. Then it just keeps going and keeps going and keeps going. So it's decreasing. So for your concave up, your slope is increasing. For your concave down, your slope is decreasing. Just between the A and B. Now you could have a graph where at some point it changes and starts increasing again, but we'll cover that a little bit later. All right. Any questions on that one?
Is that arrow what we'll see in the problem or something? Is it like up or down arrow?
Oh no, that's just my little shortcut for increasing and decreasing. Actually, I'm glad you mentioned that. I can probably, just to avoid confusing anyone who might be looking at this later. All right. Okay, so from there, we're actually going to look at the test for concavity. Okay, so once again, we're going to start off with a function that's differentiable between a and b. Oh, not between a and b, but on the interval a and b. Okay, and also we know that the second derivative has to exist. Oh, so I might as well put an and here. Ooh. Clean that up a little bit. Okay, so just from that, we know that if the second derivative is greater than 0 between a and b, then we know that it's concave up on that interval. Okay, so if you're just given an equation and you want to know if it's concave up or concave down, you don't have to draw it out. You can just use this test. Okay. Now, if the second derivative is less than 0 on that entire interval, then the graph is concave down on that interval. Now, if the second derivative equals 0, then you can't use this particular test for it. You just have to use the first derivative test. No, actually, I'm jumping one. Actually, if the second derivative is equal to 0, then it's linear. And concavity is not defined. That means it's neither concave up nor concave down. Ooh. Okay. So now if you have a graph that goes from concave up to concave down and all the way across, you don't know how many times, there's a certain point where it switches from being a concave up, and then now it picks up and becomes concave down. That's actually called your point of inflection. So you know exactly where that graph became a concave up, stopped, then it became concave down. So we can actually figure that part out. Okay, so for a point of inflection, let's say some c f of c. Okay, we don't know exactly what the c value is, it's just some value of c. is a point where the second derivative equals 0, or it doesn't exist, then that point is called the point of inflection. Which is just a fancy way, fancy way of saying the point where the concavity changes. Could be more than one depending on the graph. All right, so just to kind of give that a visualizing, let's say if you have x and some y, let's say you have a graph here, and it looks like that, where this part, you know it's concave up, and this part is concave down. At some point, it has to be okay, where does the concave up part end and the concave down part begin? So if we decide, okay, we figured it out and we know that's the point where it changes from concave up to concave down, that's your point of inflection. That's when we know your rate of change for your derivative isn't positive anymore, but it's not quite negative yet. So if it's not positive, which means it's increasing, concave up, or it's not negative, where it's decreasing, if it's just right at 0, then it's right in between where it's increasing and decreasing.